Okay. Yeah, so this was the example that I was dealing with. So now I'll go to more general results. And primarily I'll be talking about two papers. One is the paper by Austin Smith and Banks, which you have the link on the course website. And the second is a very interesting paper by Feddersen and Pessendorf, which also you have the link to the PDF on your course website. All right. Now, let's first ask the following question. In this very simple structure, right, everything is binary. Now, keep in mind that the structure is somewhat limited. There are more general voting models you can imagine, and people have written down sort of more richer versions of this kind of model. But it's a good sort of starting point to fix our intuition and sharpen our understanding. Let's first ask the question that can we devise a voting rule which will make the outcome as if all the signals were common knowledge and were pooled and was available to all the voters? Okay. Is it possible to come up with to set a voting threshold for the decision to convict, let's say, so that the fact that, these signals are private information wouldn't matter? All right. And the answer to the question is yes. Again, with this very simple binary structure, right? Most things are binary, etc., etc. Binary decision, binary signal value, binary votes, etc. We can still kind of do a lot if we could choose the voting rule in a very informed and intelligent manner. So let me show you that, the logic for that, right? For a moment, let's make some, let's think of a situation, a scenario in which all the signals were put together in one box and all the voters could see. All the voters could see all the signals, not just their own, but also the signals received by others. Maybe the voters have got together in a room and are talking to each other, right? So for a moment, let's suspend that assumption that they cannot communicate to each other. What would have happened if they could, right? Then it would basically become a decision problem. There wouldn't be any game theoretic element to it. Again, fundamentally, they have common interests, so there should be no problem for them to suppress or distort what the signal is. Right? They will say it honestly. Okay, so then it becomes a single decision problem. Yes, so there are n signals. We can see, all of us, the realization of all the n signals. So what would it take for us to be wanting to convict? Yes. Now, let's do the, suppose out of the n signals, we observe that k of the signals are guilty signals, small g, and the remaining are innocent signals. Okay, so then we'll all do a Bayesian updating. What's the probability that the true state is guilty, given that k out of these n signals have turned out to be guilty signals, right? And that's Bayes' rule. So this is Bayes' rule, and I've gone back to the more general formulation, right? The signal probability distribution doesn't have to be symmetric, right? It's the most general case. So this is the Bayes formula, right? And I can divide both numerator and denominator by the expression that you see in the numerator, and then it kind of reduces to this. Okay, now over here, you can see, so for example, if you take the symmetric case, if you look at this expression, here we have 1 minus p divided by p, and here we have p divided by 1 minus p, right? So this is a number which is less than 1, and this ratio is a number which is greater than 1. Okay, so immediately it's obvious that So this, what I was going to say is that this expression should be increasing in K, and indeed it is, right? The denominator is decreasing in K. As you're increasing K, you're putting a bigger exponent on the ratio which is less than 1. So you're pulling down the denominator, and so you're increasing the overall ratio, and it's intuitive. You know, if you get more guilty signals, we'll have a stronger belief that the defendant is actually guilty. So there's a threshold number of signals, right? There's some integer K star, so that we would like to convict if and only if the number of guilty signals is K star or more. Okay, so there's a minimum number of guilty signals that will be necessary for us to convict if all the signals were pooled together and was public information to all the voters. Now, here's a result you can prove, and the result is that, well, now let's go back to the environment that we are actually interested in, which is that all the signals are private. There's no way for voters to tell each other what the signals are. They have to decide through voting, sitting in their islands, right, looking only at their own signal and not anybody else's. So if you now go back to that environment, then this is the result. Sincere voting is informative and rational if and only if the minimum number of votes needed for conviction is exactly K star. So this magic number K star, right? If we set the voting rule there, then we can basically simulate what would have happened if the voters could talk to each other, right? Exactly the same outcome will happen. Now, suppose we set the voting rule there at K star, and suppose voters vote informatively, strictly according to their signals, right? So that is to say, when they get a guilty signal, they vote for conviction, innocent signal, they vote for acquittal. So then obviously, through the voting process, the decision will be conviction if and only if the number of conviction votes is K star or above, which implies that the jury as a whole will convict the defendant if and only if the number of guilty signals turns out to be K star or above, right? So if we set the voting rule at K star, then, and if the voters behave well, meaning that they vote strictly according to their signals and don't get into any kind of funny behavior, then we can implement this, what is called the statistical voting rule, right? Or the statistical decision rule, that conviction happens if and only if K star or more guilty signals are out there. Now, the only question is it a Nash equilibrium then? If we set the voting rule at K star, is it a Nash equilibrium for voters to vote strictly according to their signals? That is to say, informatively. And the answer is yes, right? The answer is yes. It's not hard to see. I'm trying to minimize the window just a minute. Oh, laptop is working up a little. I don't know what's happening. Okay. So the voting rule, let's call that K hat. This is the minimum number of votes needed to convict, right? If it's set equal to K star, remember, is the statistical voting rule that I discussed, right? If we were in a full information environment where all the signals were pooled together and was observable to everybody, this is the minimum number of guilty votes that would be needed. So suppose we have set the actual voting rule to this, right? And what does that mean? Now, so suppose all voters vote like this. If they see a guilty signal, they vote for conviction. If they see an innocent signal, they vote for acquittal. Suppose that's how voters behave. Now, I'm one of the voters. If I think the others are voting like this, is it my best response to also vote like this? That is the question. Okay. Now, suppose others are voting like this, right? Here's the threshold of doubt Q. Now, if I'm pivotal, what does that mean? That means that the number of guilty votes that other voters have received, right, is K star minus 1 out of N minus 1, isn't it? If I'm pivotal, that means that my vote will decide what is done. So that means that we are one vote short of conviction. Yes. So there's K star minus 1 amount of conviction votes out there, which means that there's K star minus 1 number of guilty signals, given that this is how I've assumed the other voters are behaving. So where does this place this posterior probability of guilt, given that I'm pivotal? Just conditioning on the pivotality event, where does the posterior lie? Well, it lies a little short of Q, obviously, right? So this is where pi G given pivotal is placed. It's a little below Q. Now, if I get an innocent signal, yes, then what will happen to this probability? It'll fall further.
Yeah.
Right. Now, if I get a guilty signal instead, what will happen to this probability? It'll jump up, right? It'll go up. Now, will it cross over Q? Yes, it will cross over Q, right? Because this posterior probability means that we are calculating the probability of guilt given how many guilty signals. I am pivotal means that among the others, there's K star minus 1 guilty signals. Now, if my own signal is guilty, that means altogether there are K star G signals out of N, right? And K star by definition means it's the minimum number of guilty signals which will take us over Q in terms of posterior belief. So that means once I'm pivotal and receive a guilty signal, then my belief jumps above Q. Okay, so that means that indeed, if I get an innocent signal in this situation, I would like to vote for conviction, for acquittal. And if I get a guilty signal, I would want to vote for conviction. So it is a Nash equilibrium. If we set the voting rule in this manner, set it equal to exactly K star, not any more and not any less, then it is a Nash equilibrium for all voters to vote like this, informatively, strictly according to signals, right? And then that means it will implement the kind of decision-making that we could have done if all the signals were public knowledge to everyone, okay? So all these informational barriers plays no role. If we could, in this, at least in the simple binary model, we could choose the voting rule very carefully. Yes. So the ideal benchmark is pretty good. Now, what is the problem with that? This analysis suggests that, oh, if we design institutions with care, and if we somehow can estimate the fundamental parameters like, P, Q, A, O, we can be very clever. We can choose our voting rules, etc., the rules of the game, which is to say we can design our institutions in a way that we can essentially surmount any informational problems, right? They'll go away. Now, this is too clever by half, right? Why is that? When we choose institutional rules like voting rules, yes, what should be the voting rule for a parliamentary election? What should be the voting rule for constitutional change? What should be the voting rule in juries? What should be the voting rule in committees, parliamentary committees, or um, departmental committees in universities? What have you, right? We choose a rule and apply it to many, many instances of choice. We can't go around choosing the rule every time we have to decide on something. We can't say that, well, to pass this year's budget, we will set a simple majority rule, but to pass some other piece of legislation like farmers, farm laws, we'll choose a 2/3 majority, and for something else, we'll choose an 80% majority. I mean, that's just impractical, right? So we have to choose rules which are one size fits all. And these parameters will change around for different problems. In one problem, we have some value of pi, some value of p. In another problem, the information is more noisy, so the p is lower, blah, 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 right? So how can we fine tune the voting rule like this? We have to choose one, and we have to apply that same voting rule to a whole array of problems with different parameters. So this kind of construction is just basically not practical. Yeah. But it's a good sort of benchmark to keep in mind. It emphasizes the more general point that how we choose our voting rules, where we set them, can have important consequences for decision making and the quality of decision making. That broad point should come across in this slide. Questions?
So
Yes.
some of these examples that you mentioned right now,
Yeah.
in general, they won't be information aggregation problems, right? Because you'd also have preference divergence.
Yeah. There won't be, most problems are not pure preference aggregation nor pure information aggregation. There's some element of both, I would think. Yeah.
Yes. Yes.
Um, you know, uh, Farm reform bills. Okay. People have different opinions for, you know, there are interests of many groups which come into play, right? Farmers, sharecroppers, middlemen, those of us who are not farmers, who buy food. For us, lower food prices is a good thing. For farmers, higher food prices are a good thing, etc., etc. So a lot of the conflict is due to conflicting interests and preferences. But then the issue is complex. What would happen if these farm reform acts are allowed to remain? Um, we have new marketing laws. How will it affect crop prices, volatility in prices, profit margins, etc. in the future? Those empirical issues are also debated. So think of the information aggregation problem as relating to those unsettled empirical issues about the consequences of the farm laws, right? So two people maybe, you can have one person opposing the laws and another defending the laws, partly maybe because of their different interests and preferences, but partly also because they're different understanding about how the new marketing rules will affect crop prices, mean variance, etc., etc. And that's where the information aggregation thing comes in, right? Um, all right, so let me move to now the Austin Smith and Banks paper is almost like a foundational paper. I mean, we are not going to spend too much on the paper, because the paper sort of first laid down a model or a framework in which we can analyze this sort of strategic voting. And it made a number of observations that, unlike in the earlier statistical jury theorem literature, you can't take voters' behavior as given. It depends on the context, how large is the jury, what are the parameters, what is the voting rule, etc., etc. Yeah. Okay, but moving forward, let's talk about the Feddersen-Pessendorfer paper. 1997, I think it's 98. Anyway, um, now, one of the sort of surprising result in this paper is very counterintuitive, and made the paper famous. So think of jury trials, right? If we are worried about convicting innocent people, we are worried about one of the two kinds of mistakes more than the other, right? If you become very worried about that, what would be the policy suggestion? The natural policy suggestion would be that, if I think too many innocent people are being convicted in our legal system, you would recommend to raise the bar for conviction. No? Suppose we start with a simple majority rule for juries, and you might suggest that let's pass a new law saying that 2/3 majority would be needed in the jury to convict a defendant. You may want to go all the way to unanimity, and that's where it's set in the US system, at least, that the jury has to be unanimous, this person is guilty. Yeah. Now, if there was sincere voting, that the way the jurors voted was insensitive to what the voting rule is, among other things, then raising the bar will indeed create a lower probability that innocent people will be convicted by mistake, right? It will actually bring down that probability, provided sincere voting. Yes. Now, there's no reason for us to think that intelligent voters will vote sincerely. When the bar is raised, they will take that into account in how they vote, how they convert their information into votes. Yeah. What Feddersen-Pessendorfer show in their paper is that under strategic voting and this sort of game theoretic equilibrium analysis, you can show that both error probabilities may go up if you raise the bar for conviction. In particular, and surprisingly, you can have cases, and there are examples in that paper, I'll show you that, where you raise the bar from, let's say, simple majority to unanimity. In the process, it will end up not decreasing the probability of convicting innocent people, but increasing it, right? You'll have a counterintuitive effect. And they also go on to show that if you choose unanimity rules, then the asymptotic property of Condorcet jury theorems breaks down, right? Even with very large juries, the probability of the two kinds of mistakes, convicting the innocent and acquitting the guilty, they will remain bounded away from zero, right? You won't be able to reduce those probabilities beyond a certain extent. Yeah. So you can have a counterintuitive effect, and you'll have a failure of Condorcet's jury theorem for extreme rules like unanimity. Okay. But they show also the positive result in this paper is that if you choose any other rule, and you don't have to worry too much about the rule is fine-tuned. If you choose, for example, a 2/3 majority rule, right? Any rule which is interior in the sense that the fraction of votes needed for a conviction decision is strictly between 0 and 1, right? If you choose any interior rule, then the asymptotic, and then you allow for strategic voting, then the asymptotic result of Condorcet is true, that with very, very large juries, both the error probabilities will converge towards 0. Okay, so bottom line, be wary about changing the voting rule. The outcome may not go in the direction in which you might think if you are not taking into account game theoretic effects. And avoid the corners. Don't choose unanimity or near unanimity rules, because that has terrible asymptotic properties. And interior rules, we don't have to worry too much. If we can bring in a lot of decision makers, we don't have to worry too much about customizing the rule to the parameters of the problem. Choose any interior rule. Eventually, the sheer weight of numbers and the number of signals and decision makers is going to trump everything else and will give us very efficient decision making. Right? So these are the sort of main points in the paper. Question? Let me, before getting into the maths of it, let me give you a sense of the first result, right? Why will it be the case that, if we suddenly make conviction harder, raise the bar from simple unanimity to, simple majority to unanimity, why would it ever be the case that the chance of convicting innocent people will go up? Rough reason is as follows, yes? Suppose the rule is simple majority, right? Now, every intelligent voter will take into account the fact that he's pivotal. Remember, our entire analysis is that pivotality plays a very big role. So I'll do my belief adjustment based on assuming two things. One, I'm pivotal, and second, what is my signal, right? So, when the voting rule is simple majority, what does being pivotal mean? It means that the other guys are split 50-50. So presumably some of them have gotten sort of positive signals about guilt, and some of the other have gotten negative signals about guilt. So the strength of evidence coming from the rest of the voters kind of cancels out. I'm hand waving here, but I'm trying to capture some key intuition. Everything will be made more precise. So under simple majority rule, being pivotal means that the other voters are split. The rest of the electorate is split, which means their evidence is also kind of mixed, right? So I put a lot of weight on my own signal, and therefore, my voting is very informative in that situation. Now, what if it's a unanimity rule? Unanimity rule means, let's say it's a jury of size 12. Unanimity rule means that if I'm pivotal, that means all 11 other jurors have voted to convict. Yes? So under unanimity rule, being pivotal is a much stronger signal that the defendant is guilty than under simple majority. So therefore, I may be heavily influenced by that. So under unanimity rule, when I think, oh, my vote only matters when I'm pivotal, and I'm pivotal only when 11 other people have voted to convict, and that means 11 other people think this defendant is guilty, then even if my own signal is innocent, I may overlook that and join them, because I know it's unanimity rule, or even a single vote is going to spoil the conviction decision, right? So I pay less attention to my own signal, and I kind of do something like herding. Yes. Now, of course, if you think about it, you will see that what I just said is not quite tying it up. It's not an equilibrium argument fully, because if others are also ignoring their signals, then the fact that 11 of them have voted to convict really doesn't mean anything much, right? So we have to tie it all up in some sort of equilibrium. But the sort of flavor of what I just said is going to carry over into the more careful analysis. Questions? No? Okay. So the way Feddersen and Pessendorfer do this is that they restricted it. Remember, when I walked through that example, I told you that these voting models, even these very simple voting models, have multiple equilibria, right? Some are pure strategy, some are mixed strategy, some are symmetric, some are asymmetric. So Feddersen, Pessendorfer in the paper select make an equilibrium selection right off the bat and they stick with it. Well, what is their selection? They're always going to look at the symmetric responsive equilibrium, right? So most of the equilibria are in mixed strategies, but they're symmetric. In equilibrium, all voters follow the same strategy. Okay. Yeah. So let's think about what do these, in general, what do these symmetric mixed equilibria look like? Okay. I'll choose some parameters like pi equal to half, so the priors are even, and the signals are symmetric, mirror image, right? So the two p's are the same value. This is not essential. I mean, this is to keep some of the expressions more simple, but the logic is more general. You can allow for arbitrary priors and more general signal distributions, and you'll get similar results. Okay, now let's introduce these two notations, sigma G, sigma I. So these two describe the strategy of every voter, right? Sigma G is the probability that a voter will vote for conviction after seeing the guilty signal, and sigma I is the probability he'll vote for conviction after seeing the innocent signal. Yes. So we're allowing for mixed strategies here. And as I said, just a terminology, if the two sigmas are different, then the equilibrium is responsive. Okay, let's define two additional objects which will be derived from our sigmas. Okay, what is the probability that, given the underlying state is guilty, that a particular voter following these strategies, following this strategy, will end up voting for conviction, right? And similarly, gamma I is the probability that when the true state is innocent, a particular voter will vote for conviction. So all these probabilities relate to voting for conviction, right? But under different circumstances, sometimes for guilty signals, sometimes for innocent signals, sometimes for guilty states, sometimes for innocent states. Okay, now these gammas are related to the sigmas in the following way that is quite obvious, right? So if the true state is guilty, with probability pi, the signal will also be guilty, right? And then the voter strategy says that this is the probability he'll vote for conviction. Now, if the true state is guilty, with probability 1 minus pi, the signal will be wrong and it will be innocent signal. And in that case, the probability of voting for conviction is sigma I. So then this is our gamma, right? And similarly, gamma I. Now, one thing when we're trying to understand these mixed equilibria, one thing we can say right off the bat is that both these sigmas cannot be interior. You cannot have an equilibrium where a voter randomizes after seeing a guilty signal as well as after seeing an innocent signal. Okay, why is that? Well, I can put down some math, but the reason should be obvious. Each voter is updating beliefs based on two things, being pivotal and what the signal is, right? Now, obviously, if you get a guilty signal, your posterior on guilt will be higher than if you get an innocent signal. In both cases, you assume you're pivotal. That is just common in both cases. The only difference is the realization of your own signal, right? So it stands to reason, and you can check it by doing the math, but it's not really necessary that after a guilty signal, my belief on guilt will be stronger than after an innocent signal. So if sigma I is between 0 and 1, so if I'm randomizing after observing an innocent signal, that means my posterior belief is on Q. It's exactly Q, no higher, no lower. It's exactly on the threshold of doubt. That's why I'm randomizing. That's why I'm indifferent which way I vote. Now, if I got a guilty signal instead, then I wouldn't be indifferent. My belief will be higher than Q, so I would strictly prefer to convict. And similarly, if I'm randomizing after seeing a guilty signal, that means after a guilty signal, my posterior belief is Q. So if I got an innocent signal instead, it will fall below Q, and I will strictly prefer to acquit. Okay, so we can have if there has to be mixed strategies at all, it can take one of two forms. One is sigma g is 1 and sigma I takes some value sigma, right? After guilty signal, I always vote to convict. After innocent signal, I randomize. Or it can be of the form sigma, some interior sigma after guilt and 0 after an innocent signal, right? If I'm indifferent after seeing a guilty signal, then after seeing an innocent signal, obviously, I'll strictly prefer to acquit. So basically, there can only be 3 types of equilibria in this voting model. One is strictly informative voting, no randomization. But after guilty signal, vote to convict for sure. After innocent signal, vote to acquit for sure, right? That's one type of equilibrium. Another type of equilibrium is one sigma type equilibrium, as I just said. And a third type of equilibrium is sigma 0 type. Okay. Now, you will not have more than one type of equilibrium for the same parameters, right? Once, if you fix the parameters, you'll either have an equilibrium of type 3 or type 2 or type 1, right? You won't have several of them simultaneously. That reason should be obvious to you as we go along, perhaps, but if not, ask me why. So in an exam question, you're always worrying about these things. So in an exam question, if there's a voting model, I ask you to find equilibria, et cetera, be aware that you don't have to, if you can find an equilibrium of this type, 1 sigma, the other kinds of equilibria aren't there, right? So you can forget about those. You have to just take a guess at which of the 3 types of equilibrium will arise for those parameters of that problem. Anyway, let's talk about when each type of equilibrium can arise, right? Equilibrium of type 1. There's some ugly looking expressions, but these are pretty, the meaning shouldn't be obscure. You have to calculate 2 things, right? One is, what is the posterior belief on guilt conditional on being pivotal and having an innocent signal? And what's the posterior on guilt conditional on being pivotal and having a guilty signal? Okay. If you have to have this sort of an equilibrium, then these 2 posterior probabilities have to lie on 2 sides of Q, the threshold of doubt, right? Only then will I follow this pure strategy as a voter, that after innocent signal, I don't have sufficient strength of belief that this person is guilty, so I'm happy to let him go. After a guilty signal, my strength of belief is now strong enough that I want him to send him to prison. Yeah. So these 2 inequalities are the conditions needed for this type 1 equilibrium to exist. Okay. And they're true conditions because, you can calculate both these posterior probabilities and they are all functions of parameters. So however ugly it looks, it is truly a condition on the parameters of the model. Yes. Now, we actually know when this happens. When will this type of equilibrium arise? Let me ask you the question. I've talked about it today. So let me see if anybody is awake at all. There's only one situation when we'll have an equilibrium of this type. Anyone? I mean, I've stated it in a particular way. For example, of all the voting rules, only one voting rule will trigger this sort of equilibrium or induce this sort of equilibrium.
So unanimity voting rule?
No. I mean, it may.
So majority voting.
What was all that talk about K star, the statistical voting rule? So if we knew all the signals, so out of 12 signals, we would need 8 or more guilty signals to want to convict, right? So then 8 is the sort of statistical threshold of joint decision making. Didn't I tell you at the beginning of today's lecture that if we set the voting rule at 8 votes, 8 out of 12 votes have to be conviction votes for the jury to convict. Yes, if we set the voting rule at K star, then informative voting by all voters is a Nash equilibrium. If and only if the voting rule is set at K star, right? So that was the answer I was looking for, that there's a single voting rule which will induce this sort of, and which will basically mimic full information decision making, right? For all other voting rules, we'll either have type 2 or type 3 equilibrium. Yeah. So let's focus on what the 1 sigma type of equilibrium. After a guilty signal, they will vote for conviction, for sure. After an innocent signal, they randomize, right? What will be the randomization number? Now, as always, whenever you have mixed equilibrium, you exploit the indifference property. So after an innocent signal, if they're randomizing, that means that the posterior belief after an innocent signal and conditional on being pivotal is exactly Q. It's exactly at the threshold of doubt. So that's what I have here, right? That's what this is saying. This ugly looking thing is the posterior belief. Let's take a little peek into this calculation, just a little peek, without sort of going through all the details. Where's all this coming from? Remember what the gammas are? Gammas are, if the true state is guilty and I'm pivotal, that means that the total number of guilty signals out there, the total number of conviction votes out there is alpha n. Alpha n is the voting threshold. Alpha is the voting rule in terms of proportions. So being pivotal means alpha n minus 1 number of conviction votes have been cast in by the rest of the jury. Okay. Now, what's the probability that in a guilty state, me as a voter will end up being pivotal? Well, that's this probability. That's a binomial probability, right? If the true state is guilty, what's the probability that exactly these many voters out of n minus 1 will cast a conviction vote? Yeah, no more and no less. That's a binomial probability. It will also have a binomial coefficient, which eventually cancels out when you take this ratio. That's why it's not showing up here, right? But basically, this is coming from the binomial probability that among the rest of the voters, exactly the right number will cast conviction votes so as to make me pivotal, right? And then I'm multiplying it by 1 minus p. Why? Because I'm trying to calculate my posterior of conditional on 2 things. One is I'm pivotal, and the other thing is my signal is innocent, right? So that's where the 1 minus p comes from. And in the denominator, you have corresponding expressions. So anyway, this is the Bayesian updating, and it should exactly fall on Q, right? Only then indifference will take place. So now, however cumbersome this looks, you can solve this to calculate what value of gamma G will make this equality hold. And once you find gamma G, you go back to the definition, you can back out the value of sigma, the randomization number probability. So you can calculate sigma from this indifference condition. Yeah. Now, yes, that's all. Yeah. And similarly, for a type 3 equilibrium, which is of the form sigma 0, the indifference condition, again, you have an indifference condition, but it will be after a guilty signal. So you do your posterior probability calculation after a guilty signal, conditional on pivotality and a guilty signal. And you set that equal to Q, and then again, you can do the solution with a bit of an annoying algebra. Yeah. Now, that's not the main point. let's now get to the results. Yes. Um, let's talk about the asymptotic results first. Okay. Feddersen and Pessendorfer prove two things. Two conditional probabilities don't go to, well, first of all, let's talk about interior rules. Sorry. So here's the first theorem. If alpha is strictly between 0 and 1, strictly interior rules, then Condorcet's jury theorem is valid. There will be a large enough jury which will make the right decision relative to a single decision maker. And as the jury size goes to infinity, the probabilities of the two kinds of mistakes will both converge to 0. Okay. So Condorcet is very, very happy. Yeah. Yeah. And note that the condition on the voting rule is very weak. All you have to do is, as an institution designer, as a constitution designer, whatever you want to call it, don't worry too much about where you set the voting rule. If you can put together a huge decision-making body, if you can do real crowdsourcing, choose some interior rule, just avoid the corners, just avoid unanimity rules, and you will be fine, right? The sheer weight of numbers will overwhelm the problem and crack it open, and we'll have, the crowd as a whole will be Sherlock Holmes and will identify what, whether the defendant is truly guilty or not. So,
Sir,
yes,
sir, do we expect any kind of relationship between N bar and alpha?
I mean, there will be some. It's not going to be terribly interesting. I mean, sure. Yeah. I mean, if you change alpha, you may need for some alpha, maybe even a jury of size 2 will do better than a judge. Some other alpha, you may need at least a jury of size 5. Yeah. But right. I mean, given that this asymptotic result is true, that means no matter what alpha you choose, there will always be a sufficiently large jury size which will do better than a judge, which will almost do better than God. Yeah. So yeah. Now, how do they prove the result? I mean, I'm not going to plot through step-by-step proof. I'll show you sort of two things. One is if you were to be a little more mechanical, how would you prove this? Basically, you can calculate the sigma i's and the sigma g's, right? As I said, from the indifference condition, you can calculate it. As you change the jury size, you can see the evolution of these sigmas, how they evolve. And then, you can just do it mathematically and you can check that it's true. But let me give you a more intuitive sketch of the argument here. Why is this result true? Well, there's an intermediate step that you can prove, which is for sufficiently large juries, those two gamma variables, remember? What is gamma G? It's the probability that a single voter will vote for conviction when the true state is guilty. And this is the probability that a single voter will vote for conviction when the true state is innocent. These are not parameters, remember? These are coming out of equilibrium. Yes. So these gammas change as we go from smaller juries to larger juries. What the intermediate step claims is that if you go beyond a certain jury size, these two gammas will always be on two sides of whatever the voting threshold is, alpha. Okay. Now, and the next step is to argue that if this is true for large enough juries, that means Conditional jury theorem holds. That means that, for large enough juries, error probabilities have to go to zero. Now, the second part is very simple. The second part is basically the logic that we discussed when we were talking of the statistical jury theorem, right? So suppose this claim is true. I'll come back to why it ought to be true. But here's our alpha. This is saying for n large enough, yes, the probability that any single voter will vote to convict when the defendant is truly guilty is going to be more higher than alpha. And the probability that if in an innocent state, a single voter will vote for conviction is going to be less than alpha, right? Suppose for a moment, provisionally, that this is true, this claim is true for n large enough, right? What does that mean? That means, let's say the true state is guilty. That means each voter has this probability of voting for conviction. That means that the fraction of conviction votes will be some probability distribution with mean gamma g, right? Yes. So because of noise factor, random noise, the jury still may make a mistake. Actual realized fraction of conviction votes may be short of alpha, and that probability will be given by the area under this curve, right? But the mean of the distribution, right, the expected fraction of correct votes will be gamma g, which is higher than alpha. And now if you recall the logic which I gave, now if you keep increasing n, and let's fix gamma g in one place, it'll move around a little bit, but it'll be higher than alpha. So as you increase the jury size, the distribution is getting more and more clustered around its mean. And ultimately, for sufficiently large n, most of the probability weight will be pulled above alpha because it's being pulled towards the mean, gamma g. That's the law of large numbers, right? And the same logic would apply if the true state were innocent. The fraction of conviction votes will follow some distribution with a mean around gamma I. And as you increase the jury size, you're pulling most of the probability in a neighborhood around gamma I, which is to say most of the probability will be less than, alpha. So almost surely the defendant will be acquitted, right? So if this lemma is true, namely gamma I strictly less than alpha, strictly less than gamma g, if we can prove this, okay, then it's pretty much the rest of the logic is like the statistical version of the jury theorem. Now, is there any reason why this ought to be true for large enough n? Broadly speaking, this is the reason, okay? Suppose, right, if possible, that this is our alpha, and suppose for large n, both the gammas are above alpha, let's say. It won't happen, but I'll assume, and then I'll show that some sort of contradiction will crop up. Everyone with me? Okay. So suppose this is the situation. We have a very large jury, and both these gammas are. So if the actual state is guilty, we have some probability distribution of the fraction of guilty conviction votes around gamma g. And if the true state is innocent, we have another probability distribution. Okay. Now, Um, Now, voters will follow the pivotal logic. Yes. Um, okay. So pivotal logic says that if I'm pivotal, then my belief on guilt, um, or in other words, if the probability of guilt given, um, so you can show that in this situation the uh, randomization will happen after an innocent signal. Okay, so this ought to be equal to Q. Sorry, cancel that. I was going astray. Now, what does being pivotal means? Being pivotal means that um, that uh, among the rest of the electorate, uh, the fraction of correct votes is just short of alpha, right? It's somewhere here. Yes. Now, I'm updating my posterior. I'm one of the voters. I'm updating my posterior conditional on being pivotal, right? So I'm calculating first this thing, probability of guilt, provided I'm pivotal. And then I'll add my signal. From that, I'll branch out into two probability calculations. I'm pivotal and I've got a guilty signal. And probability that I'm pivotal and I've got an innocent signal. And these two probabilities have to sort of lie on either side of Q, right? Otherwise, I'll not vote informatively at all. Okay, so here's the key sort of idea behind the sort of more careful proof. See, if the two probability distributions look like this, right? In a guilty state, this is the probability distribution of fraction of conviction votes. In an innocent state, this is the fraction. Now, if n is large, both of these probability distributions are going to be extremely centered around their means, right? So they'll have very thin tails. In particular, the amount of probability lying below alpha, right, the voting threshold, for both distributions will be small. In other words, if this is like it, then both in the guilty and in the innocent state, there's a very high chance that conviction will take place because most of the probability lies above alpha. Right? So being pivotal is a very unlikely event. So if I find that I'm pivotal, I'll be very surprised because under both these distributions, that was not supposed to happen. But what matters for Bayesian updating is which distribution makes it more likely that I become pivotal, right? That the fraction of conviction votes falls below alpha, just below alpha. So if I learn that the fraction of conviction votes in the rest of the jury is below alpha, and I look at this picture, do I think it more likely to have come from the blue probability distribution or the red probability distribution? That's the question. And the answer to that is it's overwhelmingly more likely to come from the blue distribution, right? If you take two normal distributions, for example, yes, the one whose mean is closer is a more likely place from, and both of these will become approximately normal distribution by central limit theorem. So the probability that it has come from the distribution whose mean is closer is going to be much higher than the other distribution, right? So if things were like this, if both these gammas were above alpha, then Bayesian updating will tell us that if we are pivotal, most likely we are in this blue distribution whose mean is closer to alpha, compared to the other distribution. So that means the probability on innocence will be extremely high, close enough to 1. So the probability on guilt will be very close to 0. That means my own signal will not matter. I will in this situation always want to acquit. Yes. So it's a kind of a convoluted argument which takes us to the conclusion that if both the gammas were above alpha, then each voter, after all the Bayesian updating, will want to convict no matter the signal. So we cannot have this in a responsive equilibrium. And the same logic would apply if both the gammas were below alpha, right? And that establishes that the two gammas have to lie on the two sides of alpha. And once we can prove that, we can go ahead and argue that Condorcet's theorem is correct, as I did. Questions? Think about it a little bit more, and it's a little esoteric, I realize, what I just said. It's neither completely rigorous, it's neither foolproof, nor something crystal clear. But I hope at least I gave you some flavor of the nature of the argument. Okay, I have whatever picture I drew, I put it up there. Now, what are the other asymptotic results? They prove two things. There are two kinds of conditional probabilities you can think of, right? One is, given that a defendant has been convicted, what's the probability that the guy is innocent? And then there's the other opposite conditional probability, which is probability of conviction given that somebody is innocent. And what they prove in the paper is that both of these conditional probabilities lie bounded away from 0. Right? In particular, if you have unanimity rule, so these results are about not interior rules, unanimity rules. So the rule is unanimity, something really goes wrong fundamentally, which is that the errors don't disappear even with very large juries. And so we can also say something about the strategic, the randomization value. Basically, with very large juries, even when voters get an innocent signal, they almost surely convict. And it is this which is ruining everything. You raise the bar for conviction, you make it tougher to convict. That's only half the story. When you make it tougher to convict, voters become more willing to convict. Strategic voters now know that it's tougher to convict. So if you have come close, that means a lot more votes have been cast for conviction. So the defendant is likely to be guilty with a high probability. So in the limit, each voter almost always convicts when we have unanimity rule, right? When he gets a guilty signal, he convicts for sure. When he gets an innocent signal, he convicts almost surely, right? And the rate at which this happens makes sure that these probabilities remain bounded away from 0. And so will this probability, right? That at the end of the day, if we have found that we have convicted someone, and now we are kind of recalculating what's the chance that this guy is truly innocent? Well, that probability will not converge to 0 either. Okay. Now, why is that? Once again, the rigorous proof is there in the paper, in the appendix. It's kind of a lot of detail. Let me try to give you a sense of the outline of the argument. Okay. So I'm going to try and prove one of these, which is that under unanimity the probability of innocence given conviction is strictly greater than zero, is, well, limit as n goes to infinity is strictly greater than zero. Okay. Rough idea is this. Here's the threshold of doubt, Q. Okay. And Q is sitting in the middle. Now, we know that the equilibrium will be of the sort 1 sigma. That after a guilty vote, the voter votes to convict for sure. After an innocent vote, the voter randomizes with some probability votes to convict, with some probability not. And this is what we are focusing on. Yeah. Now, if I calculate the probability of guilt given that I'm pivotal, right? That has to be strictly below Q, no matter what the jury size is. Because after getting an innocent, sorry, no, this has to be above Q. Right? Because after getting an innocent signal, this probability will have to come and become Q. Right? So this probability will be a notch above Q. How much above Q you can calculate in terms of the parameters of the model. In particular, it is independent of N, the size of the jury. Yes. If I have to be indifferent when I get an innocent signal, then before I take my signal into account, just by taking into account that I'm pivotal, my probability will have to be some finite distance above Q, right? It cannot be way larger. Yes, it's some distance which is independent of N, the size of the jury in particular. It's dependent on, just this division, this gap is a matter of just one single signal being realized. Now, if I want to calculate the probability of guilt given pivotal and the signal instead of being innocent is guilty, then that'll take me from this notch to some value here. Again, that is going to be independent of M, right? So these gaps, this is the probability only taking into account that I'm pivotal. This is the probability that I'm pivotal and my signal is innocent, and this is that I'm pivotal and my signal is guilty. These 3 points are related to each other. The gap between them has completely nothing to do with M. It is calculated based on a single signal being guilty or innocent, right? Now, of these 3 points, it's the highest point is precisely probability of guilt given conviction, actually. Right? Because the defendant is convicted if I'm pivotal. I'm pivotal means everybody else has voted for conviction, and then I get a guilty signal, and I vote to convict, and so on. Right? So therefore, this probability will have a distance from 1 which is independent of N, the size of the jury. Right? It will. How far this probability is from 1 will only depend on the property of a single signal, not how many signals are out there, right? And that tells us that, no matter, however much we increase the size of the jury, we can never push this probability beyond this particular point. And that's why the error probability is the remaining probability, right? Probability of guilt given conviction, given conviction means that we have taken the right decision, And so probability of innocence given conviction is the remaining probability. So if this remains bounded away from 1, this remains bounded away from 0. Okay. All right. So I realize the last bit is a little, you know, it's not the easiest thing to wrap your mind around. I think you should try to understand these things at multiple levels. One is sort of a broad level, and the other is a little more detailed. What is worth keeping in mind is that as we make a certain decision harder, like conviction, there are two effects. There's a direct effect. If it didn't change the behavior of jurors and voters, yes, it will lower the probability of conviction, of mistaken conviction. But we have to, as game theorists, we have to take into account how the voters are going to react to this rule change. And they react to the rule change by running in the opposite direction, by being more willing to convict. And if that second behavioral reaction is stronger than the rule change itself, then we may end up in a perverse situation where making conviction harder actually ironically makes it easier, right? And we can increase the probability of sending innocent people to jail. Okay, I'll stop there and